if you look at the details of this spin-echo correlate experiment and look at the state of the magnetization at this point, I have written the result without calculating it. And what we have is, this is what we will get at this point. We have two terms which give us magnetization along after cancellation of peak peaks. We have two terms, first two terms, which give us the diagonal peaks at zero frequency and plus minus half j. And they have ik y and ik x type of operators. Then we get these two, which give us peaks, which give us these peaks. These two and these two. Okay. And then we have the last two terms which give us peaks which are this one, and that one. So these terms, basically these terms give us cross peaks, and these terms give us diagonal peaks. And now when we apply the filter, then we will retain only single operator terms and also y terms. So this will be retained. This will be retained with multiplied by minus half, but not with the one which multiplied by Lz. That will be gone. This will be this, and this will be kept, and this will be kept, and this will be gone, and this will be kept. And so we have a much simpler situation, but the look of the spectrum is slightly spoiled. Instead of having this pattern, we have this pattern, and all the intensities are divided by 2. So we lose a factor of 2 in intensity. The pattern is changed, but the information content is not spoiled. The advantage of this experiment is that it is in pure phase. Okay. So if you are going to do a spin-echo sexy experiment, maybe it's a good idea to do sexy with a Z filter rather than sexy without a filter. Okay. Then we now come to the other experiment, extension of COSY. This is a very simple extension. We have this two-pulse scheme of COSY, in which we transfer magnetization to spins which are directly coupled to each other. But suppose we have a coupling network in which a spin 1 A is coupled to another spin M, which is in turn coupled to X. And the coupling constant between A and X is very, very small or not at all coupled. Then in a COSY experiment, we will only get cross peak between A and M and X, and there will be no direct peak from A to X. This is a limitation of the COSY experiment, because we need to have a coupling between A to X for this cross peak to appear. So the simple extension of the COSY is that you have one more magnetization transfer period before you read it. So at this point, we apply another delay in which we allow from between here and here, there was a transfer of magnetization, say for example from A to M, and then in this period we have M magnetization, which then gets transferred to X magnetization by another pulse. So we just simply apply one more pulse. So we will transfer from M to X, and the definition of this time period is very important. We have this as T1 and this as T2. So we are reading in this and this period. And this is a constant period. The value of this is important, and we will see shortly how much it should be. So we will transfer from A to X, and also similarly we will have a transfer from X to M to A. And we will get the cross peak between A and X by a relay experiment. Where is it needed? Where such a relay experiment is needed? It is needed wherever you have overlaps in the spectrum. For example, suppose we have a simple two three-spin systems And here it's an example from of a peptide. Then suppose we have an H proton, the alpha proton, and the beta proton. And we have two such systems, and alpha is exactly of the two are exactly overlapped. Then we will not be able to decide from a simple cozy experiment as to which of the two betas belong to which of the two NHs, because these are overlapped. And this ambiguity cannot be resolved. And in order to resolve this ambiguity, we need these cross peaks here from the amide proton to the beta directly, or A to X. Okay, and that is provided by the Rayleigh experiment, and we can remove the ambiguity when we have the Rayleigh peak. So in case of spectral overlap, we need to of course, if your betas are also overlapped, then you have a problem, and you then need a double Rayleigh. Okay. All right. How does this experiment work? A little more detail here, not all the algebra is necessary to understand this. What we have, I'm basically repeating what I said before, that we have a magnetization in the T1 period, it becomes an M magnetization in the tau period, and is detected as an X magnetization in the T2 period. The amplitude of the AX cross peak, before I go to the amplitude, let me say something more here, which is given here. Actually, at the application of the second pulse, there will be also several other coherences which will be generated, which we have not yet studied in so far, which are called the double quantum coherences and the zero quantum coherences, which we will study in a later lecture. And to know what exactly the amplitude of this peak is going to be here, we can suppress those paths through which this magnetization can also come back to the X spin, okay, or K to M spin. So these pathways can be suppressed by what we call as phase cycling. The 180-degree pulse you can ignore at the moment, and I will show you very shortly what is its utility. Okay, now if we ignore these paths and only look at the direct transfer from here to here, that the green path, then it can be shown that the amplitude of the cross peak, A to X cross peak, is proportional to the sine pi j KL tau, this tau, and sine pi j LM tau, that is the coupling constant between M and X spin, or the L and M spin, times sine delta L tau, and sine delta L is the frequency with which the chemical shift, M chemical shift, is evolving during tau period. And the application of the 180-degree pulse removes the dependence of this amplitude on the chemical shift of the middle spin. Okay, so that you have a simpler way of handling how much the amplitude should be. Okay. And this part which I have written down here basically is saying the same thing, except that it puts down the algebra, and I will not go through that. The pattern of the cross peak, AX cross peak, or in total of the AMX or KLM, where K and M do not have a direct coupling, is shown here. And the diagonal parts have this plus 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 character, but the cross peaks have a plus minus character. Even KL cross peak general has an antiphase character, but the KM cross peak will also have a plus minus minus plus character. And any point of time, either JKL or JLM is very small, you will not resolve them, and the cross peak will go away. Or you can see it from this expression that that you need JLM and JKL to see the cross peak. or to have a finite amplitude. This also tells us what should be our tau. How much should I take tau? And tau, most often, jkl and jlm will not be same, so you will have to choose some intermediate value of tau in which this function is optimal. But it has to be of the order of the coupling constant, inverse of the coupling constant. One of the examples of the relay where it helps out is shown here. For example, the amide to the beta peak is only obtained through a relay. What really happens is that when you take a large molecule and you have a lot of resonances, and to follow and find out all the connectivities through this ladder type of operation that I showed you yesterday, it becomes sometimes not, it often is ambiguous. And to remove the ambiguity, whether it is this path or another one which you see, another cross peak, a relay really helpful. As we put the second delay, a tau delay, the direct cross peak from the NH to the SE alpha also undergoes a change in intensity. So often the intensity of the direct peak is decreased compared to the COSY, and the peak intensity of the relay peak is what appears up. And therefore you may have to run both COSY and relay COSY, because it may not be enough to run a relay COSY experiment. Indeed, I did show no, I have not brought it today. Yesterday I showed the diagrams in which double relay COSY and relay peaks were shown in amino acid schematic COSY spectra. All right, and sometimes you cannot even get enough information by a single relay, and simply you can do a double relay experiment. And there, again, you have to figure out as to what are the coupling constants between A and M, what is between M and P and X. You can optimize tau1 for AM and MP couplings, and you have to optimize tau2 for a PX coupling. And all other peaks, as you transfer magnetization across, will go down in intensity, or it will be at least modulated. They are modulated actually. There is a decrease from T2, capital T2. There is, in general, as you are adding more and more pulses and more delays, the signal here at the detection time is going down in intensity. And you have to do all of it before it all completely decays in the XY plane. And so that is a very important thing. If you have broad lines, not enough resolution in the spectrum, it will be harder to do a double relay experiment. Okay, so far we have seen a variation of a COSY experiment and an extension of the COSY experiment. Now we come back to the COSY again and see how we can improve the cross-peak intensities in the COSY experiment. And the very first idea on that is what is called a delay COSY. Okay, as I said before, that in COSY you obtain cross peaks only for when the spins are coupled, or they have significant value of the J. And if you have very small J, very often you won't see those peaks. And this plus minus corrector is what really makes these peaks cancel away. So you need to resolve them, otherwise they cancel. This plus minus corrector can actually be removed if you give as little time for these spins to process. And if you give a little delay in the experiment, then these have different speeds in the XY plane. Maybe I should talk about it like this. They have different speeds in the XY plane, and if your delay is sufficient that the difference in the speeds of these precession is matched to the delay, they will come in phase. Okay, And that is the idea of the delay cosy. That is, if you give it sufficient precision time, that the difference in the speed of these two vectors they will catch up with each other, then you have then in the cross peak you will not have this anti-phase character, but you will have in-phase character. And then it doesn't matter whether you resolve them or not. Okay? But the amount of delay that you have to give is dependent on the inverse of the coupling constant. Therefore, if smaller is the coupling constant, the larger the delay you will have to give. And if you have zero coupling constant, you will have to give infinite delay, and so you cannot get that cross peak. So you do need the coupling constant to get the cross peak, even though it is small. So we are not violating any law here. Okay, and you can put the delay anywhere you like, either in the beginning of T1 period or in the end of the T1 period. You may also need a delay in the T2 period, but as I said before, often you can increase the resolution in the T2 period without loss of time, just by increasing the data size. If you don't do that, you should put a delay here, and that's what we did in another experiment, and we will talk about that soon. Basically, what I said, that these two vectors are processing, then we put a delay, delta, then the situation of antiphase magnetization has a cosine component, which is 2 pi j delta, which is antiphase, and a sine component, with the parallel one has a sine dependence, and this one has a cosine dependence. So anywhere you can put a delay in between, you will get actually a mixture of the two. And there is loss of signal during this delay, and you have to think about whether you can afford it or not, or whether you like to see a long-range coupling. This is a reminder to me. Okay. The same idea of the delay is used in this experiment called super cozy. At the time we had the idea, we thought we had a super experiment, and so we named it super cozy. As time goes by, it doesn't look so great, but nevertheless the name sticks. Okay, it is actually an equivalent experiment to delay cozy, except that the direction from which we approach the problem is slightly different. We're not really thinking of long-range coupling. We're thinking of normal J couplings. We do see a cross peak, but we see the cross peaks are generally smaller than the diagonal peaks. And that is because the cross peaks have this antiphase character, and we haven't got enough data set to resolve them. And that is basically the reason. So if they do have antiphase character, even though they are partially resolved, why not try to bring them in phase by putting a delay? And that is basically the idea in these experiments, which we call as super cozies. The problem is that we approach the problem from signal to noise of a 2D experiment versus signal to noise of a 1D experiment. And if you resolve these multiplets, the signal to noise of the diagonal peak is equal to signal to noise of the cross peak, and the experimental signal to noise that we expect is what we get is what we expect from theory. But if you do not resolve them, and they may not be resolved for several reasons, like, for example, you have very small capital T2, that is, the lines are broad, then you can't do anything. Lines are broad, you don't have enough time to waste, and you just can't do anything about it. And if it's a natural T2, or you have a small j, and the multiplets are not resolved, then the delay cozy is the reason. But if they're not resolved due to a poor digital resolution, that is, you collect only, say, 512 data points in T1 dimension, and you want to represent a 5 kilohertz of a spectral width in that direction, then you have 10 hertz per data point. And that's the main reason why you're not been able to resolve. Then do a super cozy or a delay cozy. And the experiment that we have suggested is just same as delay, except that we have put a 180-degree pulse in the middle of the delay. Okay, and we have suggested to do this in both T1 and T2 dimension, so to remove the antiphase corrector from the both. But as one sees that putting it in T2 dimension, you may need only a smaller delay in the T2 dimension. The 180 degree pulse has one advantage, that it refocuses field inhomogeneity loss during delta period. And it has an advantage that it retains the phase purity of the spectrum if your delay is exactly matched to 1/2J. But that rarely happens. And so you go back to taking absolute intensity plot, and then if you do not have very large field inhomogeneity in the magnet, you can remove the delta 180 degree pulse. What basically it does, as what I said in the words, that this removes the antiphase corrector from a cross peak, which was in the COSY plus minus minus plus, to a plus plus corrector, if the delay is exactly matched to the coupling constant. An added advantage of this experiment is, or added delay is, that as the cross peak antiphase magnetization is coming in phase, the diagonal peak magnetization, which was in phase, is also differentially processing and going out of phase. And so as soon as we get in phase cross peak magnetization, we get an antiphase magnetization on the diagonal. And that's very good, because we really don't want to see the diagonal.